Okay, so welcome to this presentation. This is the reason why Diana Kemmer is also on the authors list. I used Diana Kemmer's presentation from Porto of last year, which was also updated, and I put some introductory remarks concerning the recycling processes, which don't need to be known by everybody. So I start on a relatively basic level to explain why recycling is a little bit more difficult and complicated than most people think. So this is the outline. So basics of plastics recycling and EU policy on plastics in food packaging and recycling. Those are the added things. And the rest is based on the presentation of Diana from last year. So to say we have the European Green Deal, everybody has heard about this, but what does it mean with respect to recycling? The main point of the Green Deal, or the main points of the Green Deal are... Oh yeah,
on Teams they don't have the screen. Oh, no.
Yes, Teams.
Yeah, it did appear. Oui, mais I don't know where to.
Personne n'a dit que ils ne voyaient pas l'écran. Ah.
So as we all know, fully web-based is not always simple. So, okay, thank you. Good. So the outline once again, and the EU policy. So the Green Deal has several targets. One is to go to a circular economy, but this is not a real target because it's just an activity. But the main thing is to achieve the climate neutrality at 2050, which means that a big part of the Green Deal is also to achieve reduction of carbon dioxide emissions and similar emissions as well. So just to understand, because it's always the same issue, we have a lot of targets and some of them are conflicting. There's also the plastic strategy, and yes, again, there's reuse and recycling. We talked about reuse yesterday. I will talk about recycling, which, to my opinion, will be the major activity in the plastic strategy concerning packaging, because to base packaging broadly on reuse, okay, it's a nice target, but it will take a lot of effort, and recycling will come first because it's, relatively spoken, a bit easier. We have the problem in recycling that we need to have closed cycles, which means that packaging becomes packaging again. And therefore, we need also to be safe concerning the consumers. And this is what the recycling regulation tells us. It strongly emphasizes food safety, whereas we have recycling targets and also the use of recycled material in the other directives. So it's always the problem to find the right compromise between those two targets. And concerning consumer safety, it cannot be a weak compromise, it must be a good one. Good. Some remarks, basics for plastics recycling. Here's those recycling signs, the logos of the different materials. In this case, for plastics, all of the same size. You will see that we will look at this a little bit more in detail when talking about packaging, because there the materials do not have the same weight, because PET is broadly used in recycling already. PEHD is also used by part, whereas the rest in packaging is not really used at the moment. There are some projects ongoing, but no big industrial use today. So this, I hope you can see it. Okay, that's the problem of this. So we have a relatively small screen here. This is a nice picture made by the Nova Institute concerning the different ways of plastics recycling. And on the, can you see, or is there an option to have a pointer? Or is a pointer in the system as well? I know in PowerPoint it is, but
They see your mouse. They see your mouse.
Okay. Okay. Yeah. Okay. Good. Yeah. So we have the source of the plastic product, the end of the life. We have, after collection, different waste qualities, and we have the chance to recycle in different ways. Today, I would concentrate on this part here, material recycling, for several reasons. The first one is that usually overall, it leads to less CO2 emissions than the chemical recycling schemes, because they need some more elaborated technique to perform them. Second, because chemical recycling schemes require a lot more of investment, which delays the introduction. And also, chemical recycling, by the way, is not the solution of everything. So you cannot chemically recycle mixed plastic waste, which, for instance, contains polyamide and PVC and so on. So you also need some sorting there, which is not easy. And therefore, both routes are kind of conflicting once again, because chemical recycling of polyolefins, for instance, will reduce the amount of polyolefins available for mechanical recycling. Nevertheless, this is another topic. And today I will mainly talk about mechanical recycling. Dissolution is also a physical process accompanied by also a little higher CO2 emissions due to more energy usage there. But this is also a special lecture, which I would not cover today. The point, however, is if you perform chemical recycling, you have a breaking of the polymer chain and a large process which leads to monomers or oligomers, which are similar to those which are used in the production of the virgin plastics. So from the point of view of the EFSA, for instance, chemical recycling is identical or equivalent to production of new materials, whereas mechanical recycling is not. Therefore, if we talk about the problems we have to deal with recycling, we have to concentrate again on mechanical recycling. All right, some outline of the mechanical recycling. This is a simplified structure. I will go a little bit more in detail in a later slide. So first we sort the plastics. It's post-consumer waste in all cases I'm talking about. And one part for the future for the sorting will be, for instance, to sort them according to the question whether it's only food contact materials or whether it's also other materials which come into play. For instance, if you have a used oil container from HDPE, you would not like to have this in a recyclate for food use again. This is not state of the art today, but many companies are already working on that to detect where the material comes from. Then we have external cleaning, washing in the first case to remove the big contaminations sitting on top of the plastics, like food residues and so on. We have shredding into flakes. We have an option to sort the flakes and to do surface edge of the flakes for PET, especially for those which can be hydrolyzed. And therefore, this is already a part of the decontamination process. Yes, also this washing is a part of the decontamination process, but this is not so complicated, and therefore I only talk about these steps here. So the next then is extrusion. Extrusion, I expect that most of you know how an extruder works. So the material is fed in, molten, and it goes out as a strain to be granulated. But in extrusion for recycling, we also have degassing of the melt. Therefore, we have several degassing ports here at extruder for recycling, which helps to remove some of the material with a higher vapor pressure to decontaminate the product, the granules or the polymer. Then after granulation, I will show also an example of this later. We have the option for post-treatment of the granules, again by thermal and vacuum processes, which remove another fraction of the dissolved material. And in the end, our recyclate granules come out ready for use, which are decontaminated with respect to the input quality. And that what we need to talk about is the decontamination efficiency concerning different substances. So this is in a nutshell that what makes recycling interesting for food use. A little bit more in detail is this figure here. We start again, it's quite similar, but it shows the different kinds of plastic waste. We start with post-consumer waste. In Germany, we have it mostly in yellow bags. In other countries, this may be different, but nevertheless, we have a first sorting, which sorts especially according to the nature of the packaging to the outer form. So it separates films from rigids. And today, in most cases, only the very big films are recycled for other purposes, not for food, and only rigids are partly recycled into food applications. So we have two different routes here. There's the films going nearly the same way as the rigids, but on a different route. So the things which are done with them are similar, but they are separated and they are no more going together. So then we shred the rigids. I already talked about this. They are washed. This is a macroscopic cleaning process. We have a density separation. This is something I did not include in my previous slide. This already gives first separation of the type of the polymer and helps also to avoid possible contaminants. For instance, if you know that some heavier polymers like PET are less contaminated than polyolefins, you can, for instance, there already separate the polyolefins from the other polymer. We have drying and wind sifting to remove very small parts, and then we have the flake fraction. And I will talk about the flake fraction only for the rigids in the future. So we have the flakes from rigids here. This is optional sorting, again, the flakes with NER and a camera. You can, for instance, sort according to the color of the flakes, but you have also the option to sort according to the type of the polymer, once again, to remove foreign polymers again at this step. We can also then have this caustic etching, which removes the outer micrometers of a flake to remove the most contaminated part of the plastic, but this is also optional. For PET, for instance, this is not really necessary in many cases. Then we have the extrusion plus degassing, which also gives a removal on the molecular scale, as well as the caustic etching. We have the granulation and then the post-treatment of the granulation, which is also not really necessary for PET today, but for other polymers it is. And many people use it also for PET for another reason, which I will tell you about in a second. Then we have the granulate. This is an image from an EFSA report, which shows a special PET recycling step. I would only like to concentrate on step 4 here in this place, where we have the process called solid state polycondensation. There, heat treatment and application of vacuum leads to 2 different effects. One is that the polymer chains are being increased in length, because due to heat and removal of water vapor, the process of hydrolysis is being reversed and you get longer molecules and a higher viscosity in the further extrusion or injection molding process. But also during this process, you again remove contaminants. So this is recycling in a nutshell. I would then go over to the question, what is the difference between virgin and recycled plastics when we try food contact with them? And also Olivier's presentation will cover a lot of things in this direction. You see the different signs here in different size. So for PET, this is state of the art. To use recycled PET for food packaging applications. For PEHD, we already have some petitions which at the EFSA still did not achieve their agreement, but nevertheless, some countries already apply this, and some projects have been done already. Here, polystyrene, PELD, and polypropylene, they are also tried to be recycled, and we are also working on some projects on this, but this is still not industrial. And the question of other polymers is still a matter of the next decades, I would say. PVC is something different. It goes out, it's more or less being phased out in the packaging, but it's very important for the construction sector. Okay, so if we talk about food contact materials, we all have to obey framework regulation 1935-2004. You know this, and I think I can be relatively brief about this. So there is no special thing to be looked at when you use recycled material. It's just subject to the same kind of regulation. This is what this slide tells you. All material and articles are concerned. So it's not relevant whether it's plastics, it's metals, it's ceramics, and it's also not relevant whether it's recycled material or not. Good. And here we have, let's say, the major problem we have to talk about. We have, again, the 2011 for plastics, which are also valid for recycled plastics. And we have the 2022 1660 for recyclates in direct food contact. And the latter tells us we have two types of processes. And in this regulation, they concentrate on the decontamination of the process, by sure, because this is the major effect that gives the contaminants for the consumers. So there may be processes which are already authorized by EFSA, which can be operated like any other industrial process. And we have the so-called novel technologies, which need to be notified. And there's an extensive list of things to be done during the operation. So in other words, you can test your process, but you cannot test it just as you want. You have to supervise it very tightly to make sure that the consumer does not receive dangerous substances. Therefore, after a couple of years of monitoring and reporting, the EFSA could say, okay, this type of novel technology right now is no more a novel technology, but an authorized process. But you all know here in this room, but maybe the other people from hanging on the screen and several in different places will perhaps also know that these processes are quite lengthy, and the time frames given for this in the regulation are more theoretical than practical, so it always takes longer. In addition, we have the scientific opinion of EFSA, which deals with the contamination and how much can be admitted for the consumer. And then we have to compare this with the new PPWR, which in its different forms which are on the market. Today we can say, okay, there is an exemption in the PPWR for materials that are used for sensitive food products. But today we don't know whether this will be reality or not. And what we also do not know is how long this exemption will be valid. So it could be that within a couple of years, this exemption will no more be valid, and we will also have some targets for minimum recycled contents also there. So we have to be prepared to make sure that also sensible food is able to be packed in recycled materials. Good. So how do we act for virgin substances? There we have the substances, the substance list covering more than, I think at the moment, it's even more than 1,000 substances. I did not take the time to count them. In the past, it was about 900. So if you use substances that are in this list, you're on the safe side. You must not add intentionally other substances, which many people outside the EU do not know at all. You must make a specific migration test for all the substances you're using. And you can do different conditions to do so. And the limits are given in the regulation. So if you are then in the range of these limits, you're fine. What you also have to do is to give a statement on non-intentionally added substances that can be generated during the processes. For instance, degradation products generated by extrusion. So you have to investigate your materials also according to these. And then you can either measure, or if you have the knowledge for all the substances, you may be even fine without measuring by using migration diffusion modeling. The law, the regulation accepts this. But what you also have to do is to test at regular intervals to show that your assumptions are really valid. Good. The problem is that this concept doesn't work for recycled plastics. We have two things that are against this. One is that we do not know the identity of all the materials, all the substances that are in the material. So we have the contamination by the packaging, the packaged goods themselves. Let's talk about perhaps limonene for household cleaners. We have cross-contamination with other packagings which may be used for non-food products. So solvents, for instance, or chemicals would be the worst case. We have cross-contamination with other substances, the packaging constituents, which are, for instance, adhesives for multi-layer packagings, and they also create a lot of problems during recycling, especially at elevated temperatures. Things may degrade, and also people are talking about misuse of PET bottles. That's a very old story from a recipe given by, I think, BASF decades ago for mixing pesticide of them in a PET bottle. They did not talk about PET bottles, but they talked about bottles of 1.5 liters contents, which means that most people at that time used 1.5 liter PET bottles because they are so nice to do this. And if you have this E605 in those PET bottles inside, you will have residues of this. Maybe this is purely theoretical, but you have one case in a million, perhaps, where this happens. The next point is that also the concentrations are not known. So there's a lot of things that influence the concentration, and therefore you can only assume an input concentration according to a worst case assumption. So if you then have the cleaning efficiency of your process, the removal of the contaminants, then according to the worst case assumption versus the assumption for the consumer, the limits for the consumer, this gives you the requirements for the recycling process. Good, so what we can say is the target substances for the virgin plastics are well known. For recycled plastics, we have to deal with an unknown case of a mixture of substances. And therefore, we need to know on the average in a normal recycling process, which depends on the country, on the collection scheme, on a lot of things, you need to know the worst case of your contamination of the input material. And just to talk about practical experience, we are dealing since more than 20 years with this question. And unfortunately, also the EFSA uses some preliminary figures from us, which are already nearly 20 years old. And the knowledge about the true limits of contamination is still quite poor. So we need more input from there for the future. Okay, then we talk about the safety of the recycled plastics. Is it safe for contact or not? And we know for PET that it can be made. We have a lot of PET bottles. We have working collection schemes. We know that PET contains a low amount of additives. That's also a good issue. It also has a very low diffusion coefficient compared to other plastics for all kinds of substances, and therefore the interaction with contamination is low. So for PET, this is not a really big problem, but you still have to deal with this point when you put up a petition to be applied as a process at the EFSA. So the first question is, how much of the unwanted toxic substances are able to enter the material? Simple question. And this has been answered by the scientific opinion of EFSA, which is already 13 years old, but is still being used for a decision. So the first question is, how much is in the input material? How much of contaminants? And here you have to discriminate between substances which are less harmful and substances which belongs to the CRM group, to the carcinogenic, reproduction toxic, and what's the last one? Creating mutations. So these substances have a different level, which is much lower than for the rest of the substances. Our problem is we don't exactly know which kind of substances we have in there. So instead of making a full-scale analysis of all the substances you may have, which will take years and a lot of analysis, we again have to work with assumptions. Then we have the cleaning efficiency of the recycling process, which should put down this amount of contamination. Then we have to look at the consumer. Is the consumer an adult? Is it a toddler or a baby? And therefore also there we have different values. And then you can calculate with these assumptions whether your toddler or your adult or your baby receives more or less of the values estimated by EFSA. And by the way, there is a large safety margin also in this assumption. Okay, so we need a worst case input assumption. We have to measure the cleaning efficiency with a so-called challenge test. So we use an artificial contaminants in a group of artificial contaminants, and then we put them in defined quantities and test how much is in after the cleaning process. And then we need an exposure assessment, which then tells you how much those people will have as input. And this is one of the assumptions. Maximum of 5% PET bottles. This is calculated with this assumption. And for HDPE, it's even lower, it's 1%. But this assumption is not only for calculation, but this is also something that the operator of the sorting plant or the recycling operation has to make sure by the previous operations, because otherwise the assumption is no more valid. So just as an example, we expect, let's say, an input concentration, where's the arrow, it's here, of 3 milligrams per kilogram, which for PET is quite a lot. And for these CRM substances, the EFSA concluded that 0.025 micrograms, which are 2.5 nanograms per kilogram of body weight, is such a low risk that it will not be measurable by, let's say, epidemiologic studies. So this is our limit, which is not very high. And we have another assumption, which means that, for instance, a small infant of 5 kilograms body weight drinks 0.75 liters of water. And not only from a normal PET bottle, but a bottle made from 100% recyclate. So you see how many safety margins have been introduced into this calculation. There is another thing going into the other direction. They recognize that most migration models or the used migration models overestimate the migration by a factor of 5. Therefore, this can be again multiplied by 5. Also here, there's, yes, it's a little bit more than a factor of 5. So 0.1 microgram per liter for a beverage is allowed to migrate. For toddlers and adults, this is higher, but this does not really this is not really important, because if you sell a beverage in a bottle, you don't know who will drink it. Therefore, you are back again at this 0.1 micrograms per liter. And what is being modeled is 365 days, 1 year at 25 degrees C. So, yeah, it all looks quite in favor of the consumer, but it makes a lot of problems for the operator of the process. So this is in an image what is required there. And in the end, if the resulting, the modeled concentration is less than the required concentration, the process is safe, so to say. So we have the challenge test. We have to normalize this, because the challenge test is usually operated at much higher concentrations. We reduce this to the normalized input concentration. We have the cleaning factor here given by the challenge test, and hopefully we have a resulting concentration of the substances which are in there, which are lower than the concentrations modeled by the different assumptions. Okay, and this can be also used for different molecular weights. And depending on the molecular weight, you know that higher molecular weight substances have a much lower diffusion coefficient. So the required cleaning efficiency in percent of the input quantity is decreasing with the molecular weight of the substances. And this is what's being calculated. And you may estimate different applications. For instance, if you model the application in a beverage bottle, you usually have to look for 365 days at 25 degrees C, whereas if you look at a tray for a meal, which has a much smaller lifetime, you have, for instance, to model only for 10 days at 20 degrees C because it's been stored in the fridge. Therefore, the required cleaning efficiencies differ depending on the type of the product and its application. Okay, so everything put together, we have different application cases. For instance, recycling bottle to bottle, recycling bottle to tray, and recycling bottle to meat tray. Meat tray means shorter lifetime, lower temperature. And therefore, we can then say, okay, according to that, what we model in this case, we can have different limits for the contamination. By the way, we also have something in the toxicology, the so-called Kramer classes, and that what the EFSA says is a factor of 600 lower than that what's given in those Kramer classes. So again, we have a safety margin over there. So if we obey to all these rules, we have a safe recycling process. The only problem one has as a recycler is, to get these values to maintain the process. Okay, so then what is done with recycled PET? We had a lot of petitions made to the EFSA. At the moment, there's about 140 recycling processes which have been submitted there. Nearly all of them achieved their admission. Only one process was not. And the other process is depolymerization and repolymerization. Okay, on this slide, it said that EFSA rejected these petitions. Yes, they didn't reject them because they were out of the limits. They simply rejected them because this was not regarded as being recycling in the case EFSA is talking about. And therefore, chemical recycling, in spite of the fact that it needs higher amounts of energy and therefore creates more carbon dioxide or greenhouse gas emissions, we still have the positive point that they don't need this EFSA approval. Good, so I'm close to the end of my presentation. We have a framework of regulations and practice by the EFSA. We know, especially from other polymers, where I still cannot talk about because those are industrial projects which are not ready for open dissemination. We know that it's extremely difficult to meet the EFSA criteria with other materials than PET. This is, let's say, already one statement. The other statement, the other problem is what happens with the consumer. And the point is, we think, but maybe we get a different opinion later on, that the EFSA criteria in this case are too strict to be able to fulfill the recycled materials input of the forthcoming PPWR. On the other hand, we are also developing other processes which are even better in cleaning performance, and therefore maybe we meet in the middle to finally achieve a chance to meet those recycling targets. Thank you very much. And yeah, I hope I still have a couple of minutes for questions.